The next few minutes we'll talk about path planning. And really it's just a brief introduction to some concepts in path planning for mobile robots. When we talk about path planning, we mean identifying a trajectory to move the robot to a goal. There are two approaches: graph search methods and potential field planning. And both of these assume a map of the environment, and once you're given a map, you know where you are currently, you know where you want to be, you'll decide a trajectory to navigate through the map. In this video, we're going to look briefly at both of these approaches, a couple of graph search methods, and then potential field planning. Within graph search approaches, there are two concepts that are required to be mastered. First is graph construction, and then graph search algorithms. We'll touch briefly on both of these. We'll spend more time looking at graph construction and a tiny bit looking at graph search algorithms, really just one graph search algorithm. Path planning is generally in two dimensions. We're dealing with planar robots, and so the robot is reduced to a single point in the plane. Path planning approaches are gauged by the completeness of the approach. That means, is it guaranteed to find a solution if one exists? That is, if there is a path from the start to the goal, will the approach be guaranteed to find it? And then optimality. That is, does it find the best solution? And when we talk about best solution, there are different ways of considering what's best. For example, the shortest or most direct path. You could also say the safest or the most robust path. Now on to graph creation methods. The first one is a visibility graph. This is made by connecting all the vertices of the objects in the map to the other vertices that it has line of sight to, hence the name visibility graph. So you can see here our map is made up of these, or our environment has these three polygons in it, and the visibility graph connects the vertices that are visible to each other with lines. All these vertices represent the nodes in the graph, and then the lines are the connecting edges. And once we have the graph, then the graph search method will find the optimal path. Now, there are bad things and good things about all these different methods. For the visibility graph, the downsides are that it's costly in rich environments. By rich, meaning there are lots of objects with lots of vertices, so this can be an expensive algorithm. Not only do you have lots of connecting lines, but then that means that you have lots of things to search, lots of different possibilities to sift through for your optimal path. And another thing is it's dangerous, meaning that the robot goes as close as possible to the objects. So if the robot position is off, or the speed is too high, or the object isn't where you thought it is, you could end up with a collision. One method that you could use for fixing this problem is by inflating, before you create the graph, inflate the size of all the objects in your map. And then the robot will not go as close to those objects. The second of our three graph creation methods that we're going to look at is the Voronoi diagram. This creates lines that are equidistant from all the objects in the map. So if we were to draw a slope out of the plane representing the distance to an object, so if we started here, the height would be 0, and then it gets higher and higher the farther away it goes. Well, where that slope meets another slope, it'll create a ridge, and that ridge is a line of equidistant points. So the robot can follow any of these lines. And this method, like the visibility graph method, is a complete method. That means if a solution exists, this method is guaranteed to find it. On the downside, the paths are not the shortest this way. So you can see that this path is longer than the one taken by the visibility graph method. And it can be problematic with short-range distance sensors. So, whenever a robot is navigating through an environment and we have a map, we need to localize the robot in the map. So we need to have some estimate of where the robot is. So as I was saying, whenever the robot is navigating through the map, we need to know where the robot is, and that can be done through odometry, just looking at the distance the wheels have traveled and using the robot kinematics to estimate the position. But that estimate gets worse and worse as the robot moves along. So we like to update that with some exteroceptive sensor readings, and that could be a range sensor, and we can correlate those readings with the map to give us a better estimate of where we are. So when we're using or navigating a path that's generated by a Voronoi diagram, a problem is that we try to stay as far away as possible from the objects. And so if our range sensors are sort of short range, then we can be out of range of the objects and thus lose the fidelity of our position estimate. So that's just one downside to the Voronoi diagram method. But on the upside, this is really easy to execute. As long as we're sensing the objects, the robot just turns in order to keep the distance to the object on the left and the distance to the object on the right equal. And also, this can generate automatic mapping. So if you turn a robot loose in an environment with the control law we mentioned here, where it stays between the objects, then it will generate a Voronoi diagram, and from that you can back out a map of the environment, so you can come up with what the obstacles are in the environment. The final graph creation method we'll look at is cell decomposition, specifically fixed cell decomposition. Here's our map, and we overlay on it a grid of equal size cells. So that's the fixed cell. And if a cell is occupied at all, then it becomes marked as an occupied cell. And if it has nothing in it, then it's marked as unoccupied. So one bad thing about this approach is that features can be lost due to the granularity. For example, you see this opening here in the map is lost whenever we perform cell decomposition, at least with this size cell. On the plus side, this yields relatively simple path planning. For example, the grass fire algorithm is shown here, and that's one method of path planning with cell decomposition. And roughly this proceeds by assigning a number to each cell. And the cell numbers are assigned like this. We start off at the goal cell and give it a 0, and then go outward and add 1 to that number. So the cells above it and below it become 1, the cells next to it become 1. And then those cells, we find the cells above and below and next to those and add 1 to them. So this 1 becomes 2, that 2 becomes 3, we add 1 to that, we get 4, 5, 6. Once all the cells in the map have numbers, then we can determine our path very simply. The way that's done is begin at the start cell and move toward the lowest number, and just continue to move toward the lowest number until you reach the goal. Another good thing about fixed cell decomposition is it's a good way for map generation with a range finding sensor. So we can use what's called the occupancy cell approach, but we're not going to look at that now. What we will finish up with is the potential field method. And here the approach is to create a gradient U across the map. And that gradient directs the robot towards the goal and away from objects. Once we have that gradient, then the path is determined by treating the robot as a ball acted upon by a force. So we could just set the ball down at the start spot, and then it will roll towards the goal as the gradient influences it. This method serves both as path planning and control law. And we treat the gradient U as a sum of an attractive potential toward the goal and a repulsive potential away from the objects. The attractive potential goes to 0 at the goal. You can see here, this third figure, we have the potential, the attractive potential is this slope that goes up, and then once we get down to the goal it becomes 0. And then the repulsive potential is really high near the objects and 0 elsewhere. So that means that the robot will continue towards the goal until it gets close to an object, and then its path will diverge sharply, and then it will continue on towards the goal once it gets a little bit away from the obstacle. In this video, we looked at methods for creating graphs and then how those graphs were used to come up with a path to get the robot from the start position to the goal position.